Today I have a worksheet for you, so only thing to really record to go over is the two homework questions from yesterday. So this is going to be pretty quick just to go over this. Um, so let's go over it. So, question one was how fast do you need to be traveling for your Lorentz factor to be 2? So we have the formula for that. That there. Whoops. Okay, there. So basically, we're saying what is the speed as long as this equals 2. So let's sort of think about what we have here. We have 1 over this thing equals 2. So therefore, that thing, which is this here, equals 1 over 2. Then, so in other words, and then you have the square root here. So we square both sides, get rid of the square root. And therefore, 1/2 becomes 1/4. I'll keep it like that because fine. No, you know what? Is there a way to like? Yes. Stop it. What? No, stop it. Okay, there. So now I feel satisfied. Oh, jeez. So 1 minus this equals 1/4. Therefore, this is going to equal 3/4. And then if you multiply it by c squared, so that means v squared equals 3/4 c squared. And then you square root it. So v is the square root of 3/4 times c. And so then you can use a calculator to figure out what that is. 3 divided by 4, well, yeah, okay, square root of this, and you get that, 0.866. In fact, that's cosine of 30 degrees for your random information. But yeah, so 0.866c is your answer. That is how fast you have to be going. That much times the speed of light, which if you want to put that into meters per second, then that's times. That's fine. Okay, so 259. 8. There you go. That's how fast you have to be going for your Lorentz factor to be 2. Alright, so second question now. We have Milky Way is moving 600,000 meters per second towards Andromeda. And then there's the lengths and the mass and the time. And then from an outside observer, what are all these things? Okay, so first thing we have to do is find the Lorentz factor given our speed of 600,000. So we have 600 squared divided by 300 million squared. Yeah, okay. So I'm gonna scientific notation this just to make it actually easier. So 600,000 squared would be, I don't know. Let's see, that's times to the 11. Yes. 3.6 times 10 to the 11. And then this is 9 times 10 to the 16. Alright, so we therefore have 3.6 divided by 9, that's just 4. Well, 1/4. So 1/4, and then 10 to the 11 times 10 to the 16, that's 10 to the negative 5. This should be 2.4 times 10 to the negative 6, I think. Let me just double check this. or 0.4. Oh yeah, right. Yeah, okay. That's 0.4, not 1/4. Okay, but yeah, it was right about the exponent. Okay, so it's actually for now that I have it this way, I think it's better to write it like this: 4, 5, like that. Right? Yeah. Okay. So then we get 1 minus that, so 0.999996. And then, yes, go square root it. And, oh boy. I guess we'll just go to 8 there, so that's 5 nines and then an 8. That. So, our Lorentz factor of the Milky Way compared to Andromeda is that. So that's in 5, 4, and a 2. There. All right. So now we want to solve for uh, length and mass and time. So let's do mass first. So mass is always multiplied by the Lorentz factor. So we have a mass of 100 billion solar masses. Again, you don't need to convert it, so the unit can stay as solar masses. So we have 100 billion, which is 10 to the 11. Yes, 10 to the 11 times 1.12345, like that. Okay, times and you get 100 billion 200,000. So in other words, it would appear that the galaxy would have a mass, an extra mass of 200,000 suns. Length. This one is dividing by the factor. So we have with 100,000 light years. Yep, 100,000 light years. That's 10 to the 5 divided by 1.12452. So let's see. That was the original number. So then being weird about this. Okay. Yep. So it's 0.8 light years. So a fifth of a light year smaller, which don't know how far that is. I don't have a good description. I think that's like the very far edge of the solar system. I don't mean like Pluto, by the way. When I say very far edge, I mean like the Oort cloud of like the super far out comets that take like tens of thousands of years to orbit the sun or something. I think that's like a fifth of a light year or something. I don't know. I don't remember. But yeah. And then the time, that's again multiplied, and we have, what is it, 4 billion? Yeah, 4 billion. So it's 4 times 10 to the 9. This number times 4 billion. All right, and we get 4 billion 8,000. Years, okay. So yeah, while we are inside the Milky Way galaxy, it seems like the galaxy's mass is 100 billion solar masses. It seems to be 100,000 light years across, and the collision will take 4 billion years. But from outside of both the Milky Way galaxy and the Andromeda galaxy, it seems like the Milky Way has 100 billion and 200,000 solar masses of mass. It's 99,999.8 light years across, and the collision will take an extra 8,000 years. So, and again, my point back to what I said before is that this is correct. It's not like these numbers are a trick of the light or something. This is how it is actually perceived. And if you were to actually, again, do physics, for example, if you were to find like what's the kinetic energy, you would have to use this sort of new mass, right, and stuff like that. So there's a lot that you can expand on this. You can get into relativistic kinetic energy and relativistic momentum and stuff like that, and that's its own kind of beast. I think the worksheet actually. Do I give you a sort of problem for the worksheet that's has like momentum in it? I think so. I think I give you the equation. Let me if I can find it. Let's see. I have it in last year's thing for right now, so I need to switch this back. Where was this? This would be at the end here. Relativity worksheet. There it is. Let's see what we got. Yeah. So there's velocity of stuff. Okay. Yeah. Okay, so let me see how this works. Okay, so the first question here, uh, basically find the Lorentz factor of an electron that's moving at this speed. So okay, if you have that speed, what's your factor? So the observed mass. So this is saying again, this is the mass that is perceived outside of the electron, right? So basically, you're saying that this is m. We want the m prime. So you would multiply that over. Right. So then the idea is that the uh, the new electrons. So now that you have this new mass, you can calculate a new kinetic energy by using the new mass with this speed to get a different kinetic energy, and then you're comparing that to this potential energy here and seeing if that's actually enough for this to work. Second question: we have Voyager 1 moving at this speed. The rest mass as well as traveling since then. So what is Lorentz factor? So again, Lorentz factor that's just gotten from this here. Again, observed mass is also using that Lorentz factor times this. Now, so for Voyager 1's perspective, how long has it been traveling, and how far in the future is it? So for this, you have to be a bit careful. I gave you the date specifically, and so what you can do is just go on Google and type in like how many days since September 5th, 1977, and it will tell you the number of days. So you want to use that as, okay, that's the time that we have seen Voyager 1 take to go across. Now, the question I was asking, from Voyager 1's perspective, how long has it been traveling? So you have to think carefully about this. Which time are we talking about, right? Are you solving for t prime or are you solving for regular t? Okay, so think about which t you actually have and which one you want to use, and then you can kind of compare the two times to find what is actually the difference in terms of the time travel of Voyager 1. It's actually like something. It's not like, a billionth of a second. I mean, it's not like, years, but it's a non insignificant value. Let's see this one. Yes, there's its mass, and then again, similar kind of thing with the proton traveling 10% the speed of light in terms of time travel. And then this one, okay, yeah, this one. So energy consumption. Yeah, okay. So basically, when you start getting stuff that's like close to the speed of light, then the kinetic energy equation is actually this here. So it's your Lorentz factor minus 1 times the regular mass of the object, so in this case the 100 kilograms, times the speed of light squared. And so the idea for this is, because this is kind of, I remember people were trying to this question. The idea was, hey, this is how much energy you have, so let's use this energy to move this person. So therefore, you have the energy, and I'm telling you the energy equals this formula. So from that, you can solve for the Lorentz factor that way, because you know the energy, you have the formula for the energy, you can solve for gamma. Now that you've solved for gamma, you can then go backwards and solve for velocity for how fast they'd be going. And then once you have that, you can then use the gamma to find what the mass is changed to be, and then you can do the time thing here as well to figure out how that works. So yeah, that was what I was thinking of. This, you have this kind of formula there, so that's a little bit tricky for that stuff. So see, you can do with this. Again, I know that conceptually this stuff is not the easiest to follow, so you can try your best to see how this all works. But Yeah, I guess that's kind of it I got for this. Um, since you just got the worksheet to work on, so that was short and easy enough. Yes, I will put this up on Drive. I mean, well, you'll see it already. And you can get working on this. Yeah, there's not going to be a thing on Thursday, so you can spend the extra time to work on this. Friday, I'm going to get into the some concepts behind general relativity and what kind of comes from that in terms of looking at the universe in that way. We're not doing any math at general relativity because it's all terrible, but some concepts and sort of just the nature of what space is and get to some weird things. So that's fun. So we'll talk about like the fact that is space curved? What does it mean to if space is a thing, then what is not space? Um, and could you go out of space? And if you are out of space, then what are you in? And all this fun stuff that's very complicated and confusing, and people tend to kind of get existential over. So that's fun. So that's gonna be the thing for Friday. Woohoo!